In this video, we're going to look at a particular type of probability density function, one with what we call an unbounded domain. Unbounded, that's not a mistake. You don't call it unbound, you call it unbounded. Bit weird, I know. But I'm talking about the sorts of probability distribution functions like some of the exponential functions, where the domain of the part that has area underneath it is asymptotic to the x-axis, and so in theory goes on infinitely. So this particular function here, the area under that curve from 0 to infinity, if you try it on your CAS calculator, is actually 1. Your CAS calculator will tell you 1. So what I want to talk about in this video is how do you go about evaluating an integral when you've got infinity on the top as one of your terminals, or even negative infinity on the bottom, or negative infinity and infinity. Because infinity is not a number. Infinity is not a number, it is an idea about the biggest number. So you can't substitute an idea into a mathematical equation. It just doesn't work. So what do we actually do? Let's have a look. So one of the strategies that we can use is to replace infinity with a variable. In this case, you can see here I've replaced the infinity with the letter A. You can use any letter you like. And then use limits. So what I can do here, I can use this limits work that we've done in year 11 to help me to say, okay, so I can't substitute in infinity, but I can substitute in a variable, work out a formula for this thing, and then for the formula at the very end, evaluate that limit. And so that's what we're going to do. So I can evaluate the integral from A to infinity, just as if this was a number at the top, and I'm leaving the limit sitting at the front until I actually evaluate it. Because if you want to put an equals here, this line, this section has to be equal to this section to be mathematically correct. So we substitute in our values. Let me just move this over so you can see a little bit. So you can see I've substituted in A to the function for x, then I substitute in the 0, then I tidy that up a little bit, so negative e to the minus 2a stays, negative becomes positive e to the 0, which becomes a 1, and you can see I've still got my limit sitting there at the front. Okay, remember we need to leave that sitting there until we evaluate it. Let me just move this up again. And so the next bit, you can see I've replaced the e to the 0 with a 1. Now what I'm going to do is I'm going to split this limit into two limits at this plus sign here. So it's almost like expanding out the brackets, if you like. So we're finding the limit of this term plus this term, and so that is equal to the limit of the first term plus the limit of the second term. So if I had a minus in here, this would be a minus. Alright, so then I'm going to go ahead and I'm going to evaluate that limit. And to evaluate the limit, what I need to do is I need to think about the shape of the function that I've got here. What does the graph of this look like, so that I can, and the graph of this, so that I can think about what happens as that A value, which is in the position of the x, gets larger. So let's have a look at the graphs of these things. Just make this a little bit smaller so we can access the stuff further down. Alright, so here are our two graphs. So this is the graph of the first term. So it's an exponential function that's been reflected in the y-axis and reflected in the x-axis. So it's doing this. So as the x value, that should say A, as the a value approaches infinity, as we move this way, what's actually happening is that the graph itself, the y value for the function, the graph itself is getting closer and closer to 0. So when a theoretically becomes infinity, which it can't because infinity is an idea, but it'll equal to 0, so it's approaching 0. So this term here, as a gets much larger, basically disappears. For the second term, this is the graph of the function, and as the x values this way get larger and larger and larger, the function still sits at 1. So as x approaches infinity, 1 approaches 1. And what that leaves us with for our two limits is that this first limit is equal to 0. We've got plus and plus, and this second limit is 1, and that gives us our answer of 1 for the integral. So this works nicely if you're comfortable with limits. There is, if you've got it unbounded at just one end, there is a different way to do it, and I'll show you that now. If the function that you're trying to find is unbounded on one end only, there's another strategy that you can use, and that's using the idea of complementary events. So for the function here, the exponential function here, where we're looking at x greater than 0, and we're looking for the probability that x is greater than 50, then we would write that as an integral from 50 to infinity, and it would represent this yellow area here. And what the complementary property for probability does is say, instead of finding this yellow area here, what about if we found this green area here, because the green and the yellow together add to give you 1, and then do 1 minus the green area. And that way we're working with a bounded integral from 0 to 50 instead of an unbounded integral, and we don't have to do the whole limit thing. So it would look something like this. The probability that x is greater than 50 is 1 minus the probability that x is between 0 and 50. And there is our bounded integral that we can calculate quite easily without having to do all the work for the limit in the front. A much simpler way to do it, but it only works if it's unbounded on one end. So what happens if it's unbounded on both ends? Let's have a look. So if it's unbounded on both sides, and here's an example of a function that is asymptotic on the the left-hand side and asymptotic on the right-hand side, and we'll look at this function a little bit more closely when we look at the normal distribution. But you can see that we're looking for the integral from negative infinity to infinity, and there is no bounding on either side. So you could substitute in a lower bound, a letter for the lower bound and a letter for the upper bound, and then do the limits of both of those. Or there's something else that we can do which is quite ingenious. What we can do is take that integral and split it into two separate integrals anywhere you like. So anywhere along here, I'm going to pop the letter A, and then I'm going to split the whole integral into two bounded integrals, a lower half up to A, so this bit here, and then a bit above A. And then from there I can use what I used in the last section with a variable for my infinity, and there we go, a variable for my infinity instead, and use limits for both of those. Now this is, I believe, beyond the requirements of the methods course, and so I'm not going to work through anything here. I'm not going to show you how to do it. unbounded on one side, yes, I've seen that before. Unbounded on two sides, never seen it. And if we do use it at all, we're using the normal distribution, and this is a variation on the normal distribution, and we just use our calculator for that. If you are interested in more work around this and how they work, these integrals that are unbounded are actually called improper integrals, and if you Google them, you'll find a whole lot of stuff about them, and if you study maths at university, you might learn about them too.